Hello, everyone. Thank you for joining us today. This session is called AI-powered predictive analytics platform using Apache Druid. We're going to present our Druid use case here at DPI. My name is Ahmed, and I am a data team lead at DPI. Let's start off with the agenda, just quickly. Today, I'm going to be talking to you about how we're using Druid at DPI. I'm going to go through 5 use cases with Druid, where we've built around it to improve its performance and usability for our solution. Starting with our analytics platform that we offer powered by Druid, and how we have implemented a query builder to enable non-technical users to easily write their own Druid queries through our dashboards. After that, we're going to talk about how we have decreased Druid query time tenfold by building a custom result caching solution with predictive pre-cache over Druid. After that, we will talk about 2 points where we have managed to decrease our costs. The first one is by implementing a Druid segment reader to use Druid's historical data in machine learning and reduce data duplication between deep storage and our own data lake. And the second point to reduce costs was how we decreased costs by moving Druid from the cloud to an on-premise dedicated servers. And lastly, we will talk quickly about cluster monitoring and how we use Druid internally to monitor our Druid cluster performance. And but first, let me quickly tell you a little bit about us and what we do here at DPI. So starting with a little bit about that, at DPI, we offer personalization AI, as in real-time user scoring and segmentation for subscription-based businesses, basically to power their user acquisition and user retention. We also offer a variety of Druid-related products and services, including analytics platform using deep query, Druid predictive cache, and also DevOps tuning and monitoring services, along with data engineering and ML, machine learning analytics pipelines. In a few words, basically at the core of DPI is our offering of personalization AI, aka deep scoring. We receive and we get behavioral data. We score each individual user and send the scores and segmentations back to a variety of systems. Systems can be like paywall solutions, they can be like marketing automations, CRM, content management, etc. So in short, we provide centralized and unified embedded subscription scoring across a variety of channels. So how do we accomplish that? This is basically a view or simplified view of our architecture. And we accomplish that by basically collecting events through our ingestion services and APIs, where we receive them over to Kafka. We use Apache Flink along with Kafka for event enrichment, serving machine learning models. We do also custom transformations and aggregations over the events in real time. The process data is then indexed into Apache Druid for real-time analytics, along with the scoring is indexed into Cassandra for delivery of the scores. Both Apache Druid and Cassandra are served through our APIs to our dashboards and also to other integrated systems. As you can see as well, we have a pipeline from Kafka to our data lake where historical data is stored on our Apache Hadoop for machine learning model building. These models are then used by Flink for real-time scoring. So why does real-time scoring matter and why does AI predictions matter? And the answer is basically simple, is that it can increase or improve the conversion of users substantially. So as you can see here on the red graph, it measures user engagement, sorry, and the yellow graph measures propensity of users to subscribe. And the machine learning models and the real-time scorings allow you to easily identify right moments to perform certain actions. And these actions can substantially improve the user propensity to subscribe. As you can see, the spike of the user's conversion on the yellow graph. A little bit about our scale. Our system performs around 2 billion of AI predictions per month, and we score around 200 million users per month. And this results in around plus 25% uplift in user subscriptions across our clients. So with that out of the way, let's talk Druid. So Apache Druid is at the core and the heart of our analytics solutions now for over than 6 years. We provide a multi-tenant Druid cluster in our solution, and the cluster is fully managed by our team over dedicated hosted servers. Our cluster consists of 54 dedicated nodes. We receive around 100K events per second over for Druid. We have around 150 terabytes of data, live production data on historicals, and around 580 terabytes of compressed data over our deep storage. And now let's jump into the use cases that we have chosen to talk to you about it today, and where we try to customize Druid for our use case. The first use case is Query Builder and Analytics Dashboard. So for the Query Builder and Analytics Dashboard, we start with just a little bit about our users. Most of our users are agnostic to the fact that Druid is at the backend, almost sometimes with no knowledge of how to query or to use Druid. And our users typically are generally consists of 3 groups. Group number 1 is the power users. These are usually the engineers who are comfortable to learn Druid query language and are comfortable learning it. And however, they are like a very small user segment in our case. Second group is the analysts, who are comfortable maybe with MySQL and some analytical tools. And the largest group and the third group is business users, which are non-technical users. So as non-technical users are the largest group, this makes Druid query language a challenge for our solution. And we needed to think of a way to make it easy for non-technical users to use and write their own queries over Druid. And this would lead us to building our own query builder. So the query builder consists of query APIs and our own dashboards. And having the query builder here as a mediator, basically a mediator between the user and Druid, helps the user to easily use Druid. And it also enabled us to find and explore new ways to use Druid. So some of the examples of how we use Druid in our solution is through ad hoc exploratory dashboards. Second one is through enterprise KPI dashboards. Another one can be through custom products, like we have a browser extension powered by Druid to do website heat maps. And also for client-side integration, like custom content recommendation systems. Here you can see how the user can build their own queries to Druid using the Query Builder interface in our dashboards. The user can slice and dice the data using metrics, splits, filters, and conditions. All of this while specifying the dimension names and aggregations for their own liking. This is substantially easy way for any non-technical user to write their own queries and to build their own dashboards over Druid. And the query builder then translates these queries into Druid query language and forward it to Druid and gets the results back to the dashboards. And here is an example of a dashboard after the query builder have translated and forwarded the queries, and the results are back, and the results are visualized with the dashboard. And we have it like basically each query, or it's like represented by a widget over the dashboard. Here is also another solution that is powered by Druid, which is KPI dashboards that are used to track specific KPIs for enterprises. And these dashboards enable to have user management, dashboard access and privacy, and also authorization and authentications for users and APIs. And finally, another interesting example and use case here powered by Druid is the browser extension, as I mentioned, where, as you can see here, it maps the results from Druid directly on the website to the actual items on the website. And with the query builder and APIs established, doing monitoring over this query builder and APIs, it helps us to understand our system better. It helps us understand user query patterns and types, identify heavy queries, heavy users, and usage peak times. All of this information has become really handy for our important and next use case. And the next use case is custom query result caching and pre-caching over Druid. So as we know, Apache Druid provides a broker result cache and historical result cache. However, we are interested more in talking about the broker result cache in here. So the broker results cache can get invalidated too early, which makes it a little bit non-ideal for real-time streams where you can have any delayed events. And any delay events can invalidate the cache over the broker. It does not also take into account the importance of the query. Basically, how likely is it to be repeated and when? An example for that is that we can have one single dashboard that can be used by hundreds of users daily, running the same dashboard over and running the same queries, while another dashboard can be used by 1 or 2 users per day. So the importance of the query here and the importance of the weight of the query here have a huge weight to how the query is performed. On our platform as well, the built-in broker result cache had a little impact on average query execution time. And this was all of it, the motivation to build our own query cache, result query cache over Druid. So as you can see, we chose memcached to be our second layer of caching, integrating it with the query APIs for the query builder. And this enabled us to have some advantages over the native broker cache that Druid provides. So in this with this case, we have the users viewing where users have using the same dashboards, issuing the same queries repeatedly. They get served most of the cases by the cache result on the memcached, not through Druid. And the result cache does not get invalidated as often as it was with the broker cache, with real-time events, whether they are delayed events or not. And also, this gives us a complete and full control over the cache invalidation or refresh rules, giving that we can change the importance of a user, of a query, or the time period where the query is executed. Then here we have some examples for how we can customize the cache refresh over memcached to improve the query performance. So for example, for data that is older than 30 days, we can trigger them to be refreshed on a weekly basis. For data older than 3 days, they can be refreshed maybe every 24 hours. For last 1 or 2 days, they can be refreshed maybe 6 to 12 hours. And for real time, we do refresh the results in here between 5 to 10 minutes. And this basically 5 to 10 minutes, it doesn't really matter much in a large magnitude of results. And we also have an explicit real-time flag on our dashboards where when clicked, it actually skips the query cache API, the query API cache, and it queries directly Druid for the latest events with a latency of 1 to 2 milliseconds. From our monitoring also, we found that most of the queries executed at our solution are similar, but not identical. Usually the same query is executed repeatedly, but on a different time interval. So we wanted to improve on our caching even more. So we came with the idea to implement a pre-caching logic and automated cache population. So how does this pre-caching logic works? So the pre-caching logic analyzes all the recently executed queries to detect any query patterns. And by detecting these patterns, we can predict which queries are the most likely to be executed again and when they are going to be executed. Then the logic executes the selected queries before the end users. This basically happens in idle hours or over the predicted time interval that the user is expected to run the queries on. And finally, when the end user finally executes the query result is already computed and calculated and ready to be fetched from the cache. An important use case for that we have is where we have lots of analysts on a daily basis. They use the same dashboard, just viewing the results from the last 1 or 2 days. And basically, when they go in the morning and start to load the dashboard, the result is usually ready and calculated and ready for to be served by the dashboards. And here we have a graph showing how our caching and pre-caching solution resulted in 5 to 10 performance improvement, 5 to 10 times performance improvement in result fetching. So as you can see here in the yellow line here, this is execution time in seconds. And the blue line here is the request count over the days. And the peaks here correspond to the days when the pre-caching was deliberately turned off. And as you can see, the performance can vary a lot while we have the custom caching and the pre-caching layer turned on. The third use case we have is the Druid segment reader. So our data scientists rely on a daily basis on our historical pipeline to get their training data sets. This is basically from the data lake. And as user profiling is a very important aspect, historical data for training can go far back in time. And this, however, can come at a cost. Historical data, when it's stored over the data lake, it can really accumulate over time into large amounts on the long run. And deleting any historical data can be critical, as it can cause a problem if they are ever to be needed again, or if they are not backed up. So as we operate on a large scale, we store data over HDFS for training, and at the same time also we are storing data over Druid for analytics. And this is also a duplication of data footprint, and this also can be quite costly over the long run. But since all the historical data is available on Druid, how can we make use of that? Or can we make use of that for machine learning? So the idea was that we can take this data from Druid's deep storage and use it directly for building and training models for machine learning purposes. So this is where we developed a little tool to help us with that called Druid Segment Reader to use this historical data from Druid. And how it works is basically that the application starts by downloading the latest version of any requested interval by the data scientist from our deep storage to HDFS for the interval required. Then it reads all the schemas from all the segments per that interval and merges them into one schema. And this is done with the help of the class Apache Druid segment. Schemas data types then are converted into Spark data types. Segments are then unzipped, and each row is mapped into a new Spark row, and schemas rendering segments are turned into Spark RDDs. And once you have Spark RDDs, they can be written into HDFS, in Parquet, or any other formats that is required by the data scientist. So the takeaway from having this tool is that it helped us with the following. It's enabling our data scientists to access all the historical data on demand, going years back in time without depending on any other teams. And basically, this makes the data scientists happy. And it makes it possible to train on historical data, no matter how old it is, and deleting this data after training without a worry, as they are always available in deep storage. So deep storage now is actually acting as a backup for us. Lastly, and most importantly, it reduces a lot data duplication footprint by huge margin between the data lake and Druid's deep storage. Number 4, we have moving Druid from cloud to on-premise use case. So initially, when we started, we had our cluster hosted on the cloud. Scaling up the cluster in there was quite costly over time as the business was scaling up. And the biggest cost was due to network traffic caused by deep storage. Druid deep storage, as you know, is always loading and handing over segments. And this results in a huge amount of traffic, which with cloud providers, it can be comes at a great cost. So we decided to move the cluster from the cloud to dedicated hosted servers, where we manage them by our own. However, we came across something is that we wanted to stay using S3 as a file system for deep storage, as S3 supports efficient file compression in our case. And compared to other file systems, and along with that, S3 has its advantages when it comes to durability and persistence. So the challenge was, how can we keep using S3 while moving out of the cloud? So our solution was to use an on-premise Ceph object gateway storage with S3, as Ceph supports a RESTful API. Ceph file system supports a RESTful API that is compatible with the basic data access model of the Amazon S3 API. And overall, moving from the S3 to dedicated hosts, it helps us reduce our cluster costs by up to 70%, which was a big deal. And a little note in here about moving out of a cloud solution or having basically your own Ceph object gateway with S3 is that you might come with problems when using Amazon's Java S3 SDK, as it requires specifying a valid S3 region. However, if you use the APIs or use a S3 command line interface, it works just fine. Number 5, here we have cluster monitoring. So we use two methods for metric collections from Druid. The first one is by exposing metrics and alerts for Prometheus and Grafana, which is a very common and usual use case. However, it can be a little bit not scalable enough over the long run. And we use Druid in a way that we eat our own dog food through the Kafka emitter extension on Druid, where we take the events or the metrics back from Druid, push it again into Kafka, and then we index Druid metrics again and alerts back into Druid in order to analyze the cluster through our own dashboards. Using this gives us a little bit of advantages. It enables us to analyze metrics on a larger scale than where Prometheus and Grafana can enable us to do. It also enables us to analyze our APIs usage and dashboard usage through using Druid or using our own dashboards as well. And most importantly, we can do metrics transformation using Flink to achieve data sampling, aggregations, and events cleaning for these metrics. And here's an example of a dashboard that we use powered by Druid on our dashboards to monitor the cluster performance. As you can see, like plenty of metrics that you can track in there. And now it's time to wrap it up. So to summarize the takeaway from our use cases or our challenges with Druid, the first one is building our own query builder and dashboards allowed our users and non-technical users and analysts to easily write their own queries over Druid. This is without the need to learn Druid query language or to depend on any technical users on a daily basis. We also improved our query response times, 5 to 10 times by implementing a second layer of caching using memcached and pre-caching, where we can control and prepare cache results based on queries priorities, repetitions, and predictions. Third, we implemented Druid Segment Reader in order to use deep storage historical data for machine learning purposes. And this helped us eliminate data duplication and between our data lake and deep storage. And it also gave the team of data scientists the dependency to do that on their own without being dependent on engineers. We managed to cut our cost of Druid hosting up to 70% by moving it from the cloud to on-premise dedicated servers. And we remained using S3 in that case, using S3 compatible object storage over Ceph. And finally, we use Druid in monitoring Druid, and we use that by the Kafka extension, Kafka emitter extension, and Flink transformations, and it gives us a more scalable solution over the usual solutions like Prometheus, for example. Okay, and now it's time for any questions.
Okay, in the sidebar, you can find a Q&A session, Q&A chat in the sidebar. And then, I'll read them off to you.
Yes.
And so we have Cole Lakeletter. Is the segment reader tool available to the public?
It's not available to the public, but I think it's very easy to implement. As I mentioned, the pseudocode. However, if you reach back to us, I think we can help you a little bit with that.
And another question from the same person. Are the custom data cache settings configured manually, or are the configurations updated dynamically based on query traffic, deployments, etc.? Cache settings similar to refresh weekly for data older than 30 days, for instance.
Okay, so the custom caching here happens, there's two parts with it, as I mentioned. The first part is where we customize some rules manually based on our understanding of the user, the type of the user, and the time zone of the user, the use case of the user, etc. And there's a prediction part, and this prediction part is automatically where the predictions basically estimate or predict what's going to be executed tomorrow morning, for example, or what's going to be executed in the next few hours. And this is where this part is automated to refresh the cache and to prepare this data for the next execution time. So it can be a mix of both, I would say, mix of both manual understanding of the user and the use case, and also the prediction logic that comes with that.
And one final one. Are the dedicated on-prem servers for compute nodes or just for the deep storage?
It's for both, actually. So the cluster was fully hosted first on the cloud, compute nodes, all the nodes, and deep storage as well. Then we started to migrate to on-premise, and at some point we had like a hybrid model where we had the compute nodes on-premise and we had deep storage on the cloud. Then, of course, as I mentioned, the biggest cost here is deep storage because it causes a lot of network traffic, unloading and downloading the segments from deep storage, and so on. So we ended up moving all of the cluster and fully manage it on dedicated servers.
Any more questions from anybody? Feel free to put them in the Q&A section, and we'll get them answered.
So I believe, Patrick, there is no more questions, right?
There are no more, no.
Okay, sounds good. Okay, so thank you everyone for your time. I hope you enjoyed the session. Of course, feel free to reach back to me or to us with any more questions or comments, and enjoy the rest of your day. Thank you very much.